Hello, today we're going over some normal distribution practice problems and showing how you can use the functions in Desmos to solve them. First question, Dmitry Mendeleev City has had an annual rainfall of 30 inches with a standard deviation of 2.5 inches. Given that the annual rainfall follows a normal distribution, what percent of years have a rainfall greater than 34 years? Looking at this question, we can see that it is distributed normally, and we are given the mean and standard deviation, which means we can use the normal dist function. And we can just plug in these numbers we have here, mean and then standard deviation. And we can zoom in to the bell curve shown. When we're looking at what we're asking for, we are being asked for the percent of years. And that means we're going to be calculating the area under the curve of, and we're going to set the parameters, which is greater than 34 inches for this first part. We go to this cumulative property tab and the area computation. We want greater than 34 inches, so we're going to go right and then 34. That's going to give us our answer, which is the probability would be 0.055, or in percent around 5.55, or even 5.550. This next part, it's percent of years, so same thing, same area computation. Annual rainfall between 29 and 33 inches. This can be our inner function, which is between 2 points. Put 29 here and 33 here. That's about 54%, or 0.54. Next question. A survey of students' commute times at David Moss Middle School showed that they are distributed normally with a mean of 21 inches and a standard deviation of 4.5 inches. With that information already, we can do normal dist of 21, 4.5. What time represents the top 20% of commute times? Now we're looking for a data point because it says what time. It's not asking for percent or proportion. And it's actually giving us in the question a percentile. And so that means we're going to use the bounds computation function. And for the top 20%, we're going to go to right and we're going to do 0.20. And you can see the area that's shading. This is the top 20%, and this number right here is the point that represents between the top 20 and the lower 80%. So that would be your answer, 24.79. Next part asks what times represent the bounds of the middle 40% of commute times. This can be the inner function. We can type 0.40. This represents 20% in either direction from the mean, and then calculating the points that show that. So 18.64 less than x is less than 23.36. This question, on the Galileo Galilei Interstate Highway, there's an average of 28 accidents that happen per day, and the distribution of accidents per day follows an approximately normal distribution. The 90th percentile for the number of accidents in a day is 40 accidents. What is the standard deviation for this data set? For this question, we can't use the normal dist function the way we normally would because we don't have the standard deviation. You see here, the function asks for mean and standard deviation. If you just put in the mean, no standard deviation, you can't do anything with that function. And in fact, we can't even use the bounds or area computations because we already have what we want. We have the percentile and we have the data point. What we want is the standard deviation. And so what we can actually do is we can use the z-score formula for this. And we can see our z-score equals our data point minus our mean divided by our standard deviation. And we can rearrange this to solve for our standard deviation with this formula here. And what we can use to do this is because we have the percentile and the data point, we can find the z-score that goes along with that percentile. And that's going to be using this, which is our standard normal distribution, also known as our z distribution, because the data points on this distribution are equal to the z-score. So if you put in a certain percentile, and let's say it was like your data point is going to be -1, your z-score for that percentile is also -1. So data point is the same as the z-score. And we can go and put in the bounds, and we can do, from the right, we can do 0.1, which is also the same as from the left, 0.9, because that's how percentiles work. Percentiles come from the left, but you could also solve them for the right if you subtract by 1. We can take this point, 1.282 is now our z-score, and we can plug this in to this one to solve for our standard deviation. So we can say 40, which is our point, minus 28 our mean, divided by 1.282. This gives us 9.36, which is our standard deviation, which you would put in right here if you were actually showing what the normal distribution, what it was. So anyway, you can say that our sigma, standard deviation, is 9.36. Another way we can actually solve for this is using this function. You can put a variable in, and this is not how you're supposed to do it, but this is going to use regressions to kind of like cheat your way to the answer. You can use the CDF function. We're saying with the CDF from 40 to infinity, and we already know what it is. It's going to be, we're going to use this tilde. It's approximately 0.90. Oh, sorry, 0.10, because this is going to be the top 10%. The area is 10%, 0.1. And as you can see, this gives us a pretty close. It's not actually, the calculator isn't solving. It's just making a very, very close estimate, which basically gives it the right answer. But this is also our standard deviation. This is a nice trick you can use in Desmos. Know how to use this z-score, but this is a lot of times faster. So it's good to know how to use both.